Hi folks, welcome to the Math 611B Section 4.3 Concept Roundup. We're talking about inverse trig functions and their derivatives here. And in this video, we're only going to consider the derivatives of the primary trig ratios, namely sine, cosine, and tangent. We could do it for secant, cosecant, and cotangent, but I think it's just going to muddy the water here. So let's make sure that we focus in on sine, cosine, and tangent. We're going to talk about what an inverse trig function is, what the domain and ranges are, we'll get some practice, and then we'll look at the derivatives. If you look in the video description below, the whole thing's time-stamped, so if you want to skip straight to, say, practice with derivatives, check out the time and click there. The other thing that's in the description is a Chapter 4 review with some worked solutions, so you may find that helpful. All right, let's dive in here. What is an inverse trig function? So if we recall SOHCAHTOA from grade 10, say, we'd take a triangle. Let's say that this is a right-angled triangle. There's opposite, there's hypotenuse. And you might have done something like this. You'd say sine of 37 degrees is x over 10. And at some point in the process, you'd go to your calculator and evaluate what sine of 37 degrees is. Turns out it's 0.602. But when we do that sine 37, sometimes we don't think about what we're putting in. So what did I tell the calculator about? I told it about an angle. And what did it tell me? It gave me a value, or really a ratio of sides. Okay, so when you do the regular trig function, or trig ratio, you're putting in an angle. Now let's do it the other way around. We're going to look for theta in this case. This is opposite. This is hypotenuse. You might set up the following equation. Sine theta is 6 over 11. And then to find the angle, we'd go theta is the inverse sine of 6 over 11. Okay. So what are we putting into that? We're telling it about the ratio in this case. And then when I put that into the calculator, so let's try this, inverse sine of 6 over 11. The thing that it gives us is the angle. Okay, so the output is the angle. In this case, it was about 33 degrees, which, given that the diagram's kind of to scale, looks about right. In short, inverse trig functions do this. They find angles. Okay, in simplest terms. Okay, well that's fine. So they find angles. Here's the problem that arises. For an angle in standard position, this equation, sine theta equals a half, it doesn't have one solution. It has a solution here. And then it has another one over here. So we know at 30 degrees, there's a sine of a half. We can also reason out that at 150 degrees, it has a sine of a half. And then every revolution afterwards, 390, 510, and so on. And all the negative angles as well. So there are infinitely many solutions. So hopefully my calculator will give me all those infinitely many solutions. But as you've probably guessed, it won't. The inverse sine of a half, according to the calculator, is just that first angle, just the 30 degrees. So according to your calculator, inverse sine is a function. It only gives you one output value for each input. And the question becomes, why does it give you that one, exactly 30? So you might guess that, well, let's see, that is the smallest of all angles for which this is true. Okay, that tells us part of the story. I wonder what happens if I put in a negative value. So if I go inverse sine of negative a half. Gives me negative 30. Okay, so maybe they're just negative angles when it's negative. Let's keep going. We're going to investigate this a little more. What about the inverse cosine of a half? That gives me 60 degrees. Okay, that makes sense. That's the smallest angle I can think of with a cosine of a half. And then I'm going to do inverse cosine of negative a half. And I'm expecting that's going to be maybe negative 60, which doesn't actually make much sense. And it tells me 120. Hold on, there is some wacky stuff going on here. What is going on? To really explain what's happening, we have to look at the graphs of sine, cosine, and tangent, and we have to set them up so that they're invertible. Now, if you want to skip over all that and go straight to the practice or straight to the sort of end result, that's fine. But we're going to set it up so that we know where this all comes from. Okay, so if we consider y equals sine x, which looks like this, roughly. That's not a great picture of it, but even from that rough sketch, you can tell that it is not invertible because it does not pass the horizontal line test. If I draw a horizontal line here and I try and run it through, look, it touches in two places at once. That's no good. Okay, so what we want to do is we want to chop it down. We want to restrict the domain until it's invertible. So I'm going to draw a portion of this graph. It starts right here. And if I draw just this much, which is until pi over 2, and just this much, which is until negative pi over 2, then I end up with something that is invertible, that does pass that horizontal line test. This would go from negative 1 to 1 in its y's. So this is a portion of y equals sine x that's invertible, and we're talking here about a domain from negative pi over 2 to positive pi over 2. We're talking about a range from negative 1 up until 1. If we want its inverse, well, its inverse is just switching x and y. And we could write that as y equals inverse sine of x. And when you take an inverse, all you need to do is switch the x and y in every coordinate. Okay, so on the original, I have the point negative pi over 2, negative 1. Well, let's see. On its inverse, that will go negative 1, negative pi over 2. The point 0, 0, the origin, switch x and y, just gives you 0, 0. And this point over here is pi over 2, 1, so it becomes 1 pi over 2. And it looks like this. It's the mirror image through a diagonal line. Okay, and when we invert, all the x's become y's, so, and vice versa. So the domain now is from negative 1 to positive 1. And the range is from negative pi over 2 to pi over 2. Okay, that's great. So we know something about what the graph is going to look like. What does it mean? Here's the basics of what it means. You can put values from negative 1 to 1 into sine x. And what you'll get out are angles from negative pi over 2 to positive pi over 2, or negative 90 to 90 inclusive. Okay? So in other words, the output from inverse sine is angles in quadrants 1 and 4, from negative 90 to positive 90. So just to illustrate that, if I do the inverse sine of a half, okay, inverse sine can only occur in these quadrants. Oh, it's a positive sign, so it must be in this quadrant, in that first quadrant. And you're asking yourself, what angle has a sine of a half? We know that that angle is 30 degrees. Or we could write it as pi over 6. For the next one, the inverse sine of negative a half, again, we've got just these two quadrants to pick from. Obviously, if sine's negative, it's going to be down here. And we're still talking about something that has a sine, basically, of a half, or a reference angle of 30. We call this angle negative 30 because it has to fit in this range of values. That is what going through that whole process of inverting the graph tells us. Now we're going to do the same for cosine and tangent. Okay, so if we consider cos x looks like this. Again, this is not a perfect graph, but you can see right away that it fails the horizontal line test. It's not invertible. I could try and do the same and use that negative pi over 2 to pi over 2 region that I used for sine, but that's no good either. That still fails the horizontal line test. So what I'm going to do with cosine to try and get as much of it as possible is start right here at 1 on the y, and I'll just draw until I start doubling back. Still passes the horizontal line test right up until pi. This would be pi over 2. Okay, so the invertible domain is going to be from 0 up to pi, and the range that results is from -1 to +1. The inverse of y equals cos x is x equals cos y, or y equals the inverse cos of x. And again, we take every point and we flip them. So this one here was the point 0, 1. It's going to come and be 1, 0. This point right here, this was pi over 2, 0. So it will become 0, pi over 2. And this one here is pi, -1. It will become -1 and pi. And again, as long as I connect these so that they really look like inverses of each other, it looks like this. So on this graph, this inverted graph, we've got a domain from -1 to 1. And we've got a range, in this case, from 0 up to pi. Sorry, that should be y. So things are a little bit different with the cosine, and that's why we had that difficulty in figuring out what's going on with cosine of negative values. So the meaning here is that you can put in any value from -1 into inverse cos of x. And what you're going to get out are angles from 0 to 180, or 0 to pi in radians. In other words, the output is going to be angles in these two quadrants, 1 and 2. Okay, so if we look for the inverse cos of 1, again, it can only be in these two quadrants for inverse cos. It's going to be positive, so that's the first quadrant. The angle that has a cosine of 1/2 is 60 degrees, or we can call it pi over 3. The cosine of -1/2, out of these two quadrants, cosine is going to be negative over here. It has a reference angle of 60, but in standard position, this angle, we call it 120, or 2 pi over 3. And that makes sense because our output needs to be between 0 and 180. And we actually already did this one earlier. You can see there, we typed in inverse cos of -0.5, and it gave us 120. So we're matching up with our calculator's interpretation of inverse cosine. Lastly, we're going to consider y equals tan x, and that has asymptotes. So here's one cycle. But then it just goes and does it again, and more asymptotes. -pi. So still trouble. This does not pass the horizontal line test, but it's pretty easy for us to find an invertible portion on this. You just take one cycle of the graph. And the easiest cycle to take is this one right around the origin. Okay, so it goes from -pi over 2 to pi over 2. Here, the domain doesn't include those end values because they're asymptotes. And the range is all real numbers. If we invert it, we'd get x equals tan y, or y is the inverse tan of x. So all those vertical asymptotes are going to turn into horizontal ones. And the point 0, 0 will stay the same. And I'm trying to do this with as few individual points as possible. Just the basic shape. Okay, we could find some individual points on the original, but there's the shape we're looking at. And it's enough to tell us that our domain is now all real numbers. And our range is from negative pi over 2 to positive pi over 2, not inclusive. Okay, you can't actually get out pi over 2 or negative pi over 2. So again, what does that mean? You can put anything into inverse tan x. And what you'll get are angles from negative 90 to positive 90. In other words, angles that are in quadrants 1 and 4. Just like sine, or like inverse sine. Okay, so let's try a couple little examples here. The inverse tangent of 1 has to be in one of these two quadrants. Tangent's positive, must be over here. This is the angle 45 degrees, or pi over 4. Okay, that fits into this range of values. The other one, inverse tan of negative 1. Tangent's negative, it's got to be in this quadrant. And we call this angle, it has to be something between negative 90 and positive 90. So we call it negative 45 degrees, or negative pi over 4. Okay, so to sum this whole thing up, inverse sine and inverse tan give angles in quadrants 1 and 4. Inverse cosine gives angles in quadrants 1 and 2. Because those kind of look like exponents, well, they look exactly like exponents, but they don't mean exponents, there's alternate notation that you should be aware of. Inverse sine is typically called arc sine. Inverse cosine is called arc cos. And inverse tan is called arctan. So either way that they're written. But you should be aware that inverse sine of theta does not equal 1 over sine theta. They're different things. This means inverse, not a power. And that's one of the reasons we have that arc nomenclature, so we don't have that confusion. Okay, so that's the background on why things are the way they are. Now let's just try and find some of these values. So if we're just looking for the inverse cosine, sine, or inverse tangent, the question is, what's the angle? So what is that angle with the cosine of root 2 over 2? It's cosine, it's got to be in one of these two quadrants, and it's positive, so it's over here. And I know that the angle that has a cosine of root 2 over 2 is 45 degrees, or you can call it pi over 4. Okay, inverse sine. Inverse sine existed in these two quadrants. And again, it's positive, so I know it's going to be in this quadrant. Root 3 over 2, I know that that is 60 degrees, or pi over 3. And if you don't know those, then you either got to get it together with special triangles, or the hand trick, or with a table, or some way of knowing those basic values. All right, arctan of negative root 3 over 3. So we're talking about tangent here. Has to be in one of these two quadrants. And it's negative, so it must be here. Okay, and we're talking about a reference angle, if it's root 3 over 3, of 30 degrees. So we call this angle negative 30 degrees, or negative pi over 6. Those are the basics of going ahead and finding the corresponding angle. We can also take a look at this in the context of some triangles. Here we're told that theta is the inverse sine of 12 over 13. So I'm going to draw that triangle. Here's theta. And we're talking about sine, so this is opposite. over hypotenuse. So I'm going to draw it, and I've got 12 for my opposite. I've got 13 for my hypotenuse. Right away, I know that the sine of theta is 12 over 13. If I want to find the cosine of theta, then I've got to go ahead and find the remaining side. Now, it shouldn't be a big deal for us to find that remaining side. We just need to use Pythagorean theorem. So we'd say 13 squared equals 12 squared plus, I don't know, let's call this b squared. So 169 equals 144 plus b squared. 25 equals b squared. Or b is 5. There's the triangle, all completed. And on there, we know this is what we call the adjacent. This is the opposite. And this is the hypotenuse. So the cosine is just 5 over 13. The tangent is opposite over adjacent, so 12 over 5. To find the other ratios, cosecant theta, well, that's just the flip of sine theta. So 13 over 12. Similarly, secant theta is the flip of cos theta, so it would be 13 over 5. And the cotangent is the flip of tan theta. So 5 over 12. We might end up with these cases where we have sort of nested bits of a regular trig function and an inverse. And in some cases, there are two ways that we can do it, but there's one way that's more flexible than the other. So here I'm going to show you the easiest way to do this one because it happens to have a special angle. This is the cosine of the inverse sine of root 3 over 2. This inverse sine of root 3 over 2, that's easy for us to figure out. That is the angle 60. So we're talking here about the cosine of 60 degrees, and we know that the cosine of 60 degrees is a half. That method relies on us actually knowing what the inverse sine of that ratio is. The other way that we can do these types of questions is to set them up with a triangle. And this is more flexible. So this is going to be our angle that we choose. We're talking about inverse sine here. So this is the opposite. This is the hypotenuse. Okay, so opposite's root 3, 2. And all we're really looking for is the cosine in that triangle. So here's opposite. Here's hypotenuse. We're wondering what that final side is, and we can obviously use Pythagorean theorem. And again, I'm going to call it b squared. So that's 4 equals 3 plus b squared. B squared equals 1, or b equals 1. Once you have the triangle all set up, we're just saying, oh, the cosine is, the cosine of theta in that triangle is 1/2. Okay, so that is our final answer either way. So in this case, maybe method 1's better. But in the next one, method 1 is not going to be a possibility, because I don't know what the arcsine of 2/5 is. That's not one of my special angles. So if we want to do this one, we'll set it up the same way. My diagrams are not really to scale. I'm just going to do my best here. But I'm talking about something with an opposite of 2 and a hypotenuse of 5. Here's my angle. Opposite and hypotenuse. In the end, I want to figure out the tangent in this triangle. So to do that, I will need the last side. And I'll just say, okay, well, 5 squared is 2 squared plus b squared. Or 25 is 4 plus b squared. Or b squared is 21. Or b is exactly root 21. Okay. And I will ask you for these answers exactly. So it won't be okay for you to go tan of the inverse sine of 2/5. You can't just do that in your calculator. So now that we've got the triangle done, we just say, oh, the tangent is opposite over adjacent. 2 over root 21. Now, you can rationalize that, but I'm fine if you don't. So we can leave it that way, 2 over root 21, or you can call it 2 root 21 over 21. Doesn't matter. Let's do one last one. We want the tangent of the inverse cosine of x. So here, I'm going to draw another triangle, inverse cosine of x. So this must be adjacent. And what is it over? It's over 1. So that's the hypotenuse. So in this triangle, here's what we know. Adjacent is x, hypotenuse is 1. If we want the tangent, we're going to need opposite over adjacent. So clearly, we're going to need this third side. So I can say 1 squared equals x squared plus, again, I'm just going to call it b. So I get 1 minus x squared equals b squared, or b squared, b rather, is square root of 1 minus x squared. Okay, there's my opposite. There's my adjacent. And the expression that will come for the tangent, the tangent is opposite over adjacent. Okay, that's the relationship between them. So we've done a bunch here with working with inverse trig ratios. Now let's take a look at differentiating them. So proving the derivatives of inverse trig functions. We're going to start with sine. I want to find the derivative of the inverse of sine x. Now that is equivalent to saying sine y equals x, or x over 1. Okay. So if I could find y prime using that thing on the right, that might help me. And the easiest way for us to do these proofs is to set up a triangle that has these properties. So the angle we're interested in, we're calling y. This is going to be our opposite of x, and our adjacent, or not our adjacent, I'm sorry, our hypotenuse of 1. Okay. And this expression on the right, we're going to differentiate. And we'll differentiate implicitly with respect to x. So the derivative of sine y is cos y. We know that. But I differentiated something with a y, so I need a y prime. The derivative of the right, well, that's the derivative of x. So that's just 1. In other words, y prime is 1 over cos y, which is true but unhelpful. We could figure out what the cosine of y is, though. Cosine of y is just adjacent over hypotenuse. So I've got this triangle. If I could just figure out what the adjacent is, then that would help. So 1 squared equals x squared plus b squared, or b squared equals 1 minus x squared. b is root 1 minus x squared. There's the last side, and that's the adjacent. Now I can just sub that in. Cos y means adjacent over hypotenuse. So I'm going to get 1 over adjacent, which is root 1 minus x squared, over hypotenuse, which is 1. So by the time I'm done, I end up with this expression. Meaning that if y is the inverse sine of x, its derivative is 1 over root 1 minus x squared. We can similarly prove the other ones, and we'll do it fairly quickly here, but feel free to skip ahead if you've got the idea. So if I want to do it for cosine, I can say, well, I would really like to differentiate the inverse cosine of x. That is an equivalent statement to cos y equals x, maybe over 1. Now I'm going to set up a triangle that represents that. So in this triangle, x will be the adjacent, and the 1 will be the hypotenuse. Y is the angle. So adjacent is going to be x, hypotenuse is 1. And now we'll differentiate implicitly with respect to x. So that'll give us negative sine y times y prime equals, derivative of the right is just 1. I'm going to deal with that negative, so I'll just call this sine y times y prime equals negative 1. Or y prime equals negative 1 over sine y. Okay, now I just want to find out what sine y is. And to know that, I'll need to know the last side in the triangle. So here's hypotenuse, here's adjacent. Oh, let's find our opposite. And again, it's the same sort of gag. We're looking at Pythagorean theorem. 1 squared equals x squared plus, again, I'll call this b squared. So 1 minus x squared equals b squared. Or b is root 1 minus x squared. And sine, we know, is opposite over hypotenuse. So y prime is going to be negative 1 all over opposite, which is root 1 minus x squared, over hypotenuse. Or you might write the derivative this way. It's negative root 1 over root 1 minus x squared. Okay, it's the same as the one for inverse cos, but with a negative. So for an inverse cosine, there's the derivative. Lastly, we might say that we want to differentiate the inverse tangent of x, okay, which is equivalent to saying tan y equals x over 1. So there's our opposite. There's our adjacent. Y is our angle. Let's go put this in the triangle. So y is the angle. Opposite's x. Adjacent's 1. So this is a little bit different for finding the final side. Let's differentiate and then see what we need to figure out. So we'll differentiate. And we know that this is secant squared y times y squared equals 1. Oh, times y prime, rather. Y prime is 1 over secant squared y. And now it just falls to us to figure out what secant squared is. Well, to find that out, we're going to need to know the hypotenuse. So we've got opposite, we've got adjacent. The hypotenuse is over here. I can call it c. So c squared is 1 squared plus x squared, or c squared is 1 plus x squared, or c is root 1 plus x squared. It's bigger than either of the other sides. If we want to use that in secant, well, secant is the friend of cosine. Cosine's adjacent over hypotenuse. Secant is going to be hypotenuse over adjacent. And it's going to need to be squared. So we get 1 over hypotenuse over adjacent, which is 1, all squared. And all that's going to do is get rid of the square root. So we get y prime is 1 over 1 plus x squared. Or some people write it this way, x squared plus 1. Doesn't matter. So there is the derivative of inverse tan. Let's sum them all up. So now there are rules for us. Arcsine is 1 over the square root of 1 minus x squared. Arccos is negative, the same. And arctan is 1 over 1 plus x squared, or x squared plus 1. Whichever way you like it. Now that we know those rules, let's put them to use. So if we want to differentiate arcsine of x squared, we need to make sure we don't forget the chain rule. Okay, so if I wrote down the rule for arcsine, it's this. If y is arcsine x, then the derivative is 1 over the square root of 1 minus x squared. Here it's not an x, it's an x squared. And there's going to be chain rule here. There's an outer portion, which is arcsine, and there's an inner part, which is the x squared. So let's deal with the outer first. That's going to be the new rule that we know. The derivative is 1 over the square root of 1 minus, and here instead of an x, you have an x squared. So it'll be x squared squared. I'm just subbing x squared into the formula. But that's not all. We also need to multiply by the derivative of the inner. So we've done the derivative of the outer. Derivative of the inner is 2x. And when we put that all together, we're going to have 2x all over the square root of 1 minus x to the 4th. Okay, there's our derivative, or rate of change, or slope on the original one. Let's try the same thing here with something that's a little more involved, but it's got inverse cos. Okay, remember, that is not equal to 1 over cos of root x plus 1. We have that inverse cos, so we need our rule. The derivative of arc cos, which is the same thing, is negative 1 over square root of 1 minus x squared. Okay, let's work this through. So that 2x is by itself. We differentiate it, we get 2. Now the next one, 3 is a constant multiple, or a coefficient, so it'll stay out front. And here I'm going to have chain rule happening. The first thing I have to deal with is my arc cos, which turns into negative 1 over the square root of 1 minus. Okay, if it had just been x, it would be x squared. Here it's root x plus 1, so it'll be root x plus 1 squared. Okay, that deals with the inverse cos. Now I think of this thing here as x plus 1 to the half, and its derivative is going to be 1/2 x plus 1 to the negative 1/2. And I could also think about going further in. If I go to the innermost part, which is this x plus 1, that has a derivative of 1 from the chain rule. Okay, let's keep working here. So we'll simplify this a little bit. We've got 2 plus 3 times negative 1 over the square root of 1 minus, now let's check this out, square root then squared, so that's 1 minus x plus 1. They undo each other. By a half, well really this is 1 over 2 root x plus 1, and that 1 we don't need. Simplify a little further. So 3 by negative 1 by the square root of, let's see, that's 1 minus x minus 1, so negative x. And 1 over 2 root x plus 1. So putting it in nicest form, it will look like this. 2 minus, there's going to be a 3 on the top. On the bottom, there's going to be a 2, a root negative x, and a root x plus 1. And there's our derivative. Okay, so we really need to watch out for that chain rule. Let's look at one quick application here. We've got a surveillance camera mounted to a 10-meter pole, and it swivels theta radians to track the motion of a car. So I'm going to draw this out. There's a 10-meter pole. Here's the camera on top. And there's a car that's driving away. Suppose the car is x meters from the base of the pole and driving away. So theta is going to be the angle that it swivels through. If the car was right at the pole, then theta would be 0, and then it gets bigger and bigger. we'll assume that the pole is straight up and down, it's vertical, and that the road is flat. We're going to make an equation for theta in terms of x. So the last question here is, where does x go? The car is x meters from the base of the pole, so this side here must be x. So you can see that we know opposite and we know adjacent in this setup. So the obvious choice would be tan. Tan theta is x over 10. Or theta is the inverse tangent of x over 10. Now we're going to differentiate it. d theta by dx. So differentiate. We have the rule for tan. And here was the rule for tan. If y equals inverse tan of x, then y prime is 1 over 1 plus x squared. Okay, so for us, that's going to be 1 over 1 plus x over 10 squared. And then times the derivative of the inner here, which would be 1/10. And if you have trouble seeing that, you can always think of x over 10 as 1/10 times x. Okay, the derivative of that is clearly 1/10. If it had been 2x, it would be 2. Okay, we can simplify this if we like. There are a bunch of ways that we could write the final answer. I'm okay in this case with us having some nested fractions. So this is 10 times 1 over x squared over 100, or 1 over 10 plus x squared over 10. Okay, those are all equivalent statements. So the last thing we're asked to do is interpret d theta by dx when x is 30. And there's our picture up there. So I'm just going to throw a 30 into d theta by dx. It'll give me 1 over 10 plus 30 squared over 10. Or 1 over 10 plus 900 over 10. Or 1 over 100, or 0.01. Now remember that the Leibniz notation tells us about units. d theta, that was in radians. And x was in meters. So whatever this means, it's measured in radians per meter, for sure. And here's the interpretation. When the car is 30 meters from the base of the pole, the camera is swiveling. Swiveling. At a rate. We're finding rates when we find derivatives of 0.01 radians per meter. And the meters are the meters traveled by the car. And as the car gets further and further away, that rate is going to decrease. Now, we probably want a rate in terms of time. We're not quite there in terms of the amount of work we've done, but we will get there when we look at related rates. So this is kind of a precursor to that. The applications are going to ramp up once we hit Chapter 5. But this gets us through what's going on in inverse trig and, functions and their derivatives. I hope that you found it at least somewhat helpful, and there are some resources in the video description below that you may find helpful. Take care.